So the last class we started talking about stoichiometry, to pronounce it correctly, and we talked about how much of a chemical takes part in a reaction. We talked about relative atomic mass, and those are just the masses that are of the elements that are given in the periodic table. And of course, we can use those masses to figure out the relative molecular mass, the term used for covalent compounds, and the relative formula mass, which is the term used for ionic compounds, uh, putting those together just like we are doing over here for carbon dioxide. All right, then we talked about the mass of a single atom, and then taking the relative atomic masses to be actual masses in grams, and then okay, fine, how many particles are there? So we came across Avogadro's number, which is 6.02 into 10 to the power 23 particles in what is called a mole, right? So taking the relative atomic mass of an element or relative molecular or formula mass of a compound to be the mass in grams, that much mass correlates to 1 mole of that substance, that chemical, which contains 6.02 into 10 to the power 23. So it's not dictated by the mass itself. As you can see, we have over here carbon, oxygen, carbon dioxide, and water, and right, any other like NaCl or CuCO3. So right, 58 grams of sodium chloride is 1 mole, which has 6.02 into 10 to the power 23 molecules, and 100 grams of calcium carbonate is 1 mole of calcium carbonate, is the mass of 1 mole of calcium carbonate, and it has 6.02 into 10 to the power 23 particles in it, in this case molecules, right? So we talked about that, and I left you with a question like this, so erase that, and we are going to continue. So I'm going to focus on like include calculations, because this chapter is all about calculations. So starting off, I'm taking these from the book, right? They're worked out, but doing them on the whiteboard with you guys will hopefully help clarify the concepts. So here's a question, right? What are the number of particles in 0.5 moles and B 0.1 moles of carbon, just carbon? Right, now, because we're talking about number of particles, 1 mole of carbon is how many particles, Sobia?
Sorry,
1 mole has how many particles?
one.
Oh, come on.
Sorry. Oh yeah. Mm, 6.02.
Just 6.02?
Yeah.
What about the 10 raised to the power 23?
Yeah, and that too.
That huge exponent.
Oh yeah.
It's like you saying, oh, zeros don't matter.
Well, they don't they?
You do know the answer to that.
Oh yeah.
Right, so 1 mole is those many particles, and so is for part A. Right, it's pretty simple. 0.5, how many particles does it have? So that's 6.02 into the 10 to power 23, not 22, not 223, 23 multiplied by 0.5, and that gives you, well, obviously half it, so 3.01 into 10 to the power 23. Right? And because we're talking about carbon as an element, we're talking about atoms. Okay. Then you've got 0.1 mole. So similarly, 6.02 into 10 to the power 23 multiplied by 0.1, and that gives you, right, 6.02 into 10 to the power 22. That's simple.
Yeah.
Okay, another question. They're asking you, what is the mass of hydrogen produced? Right, the situation is 46 grams of sodium was reacted with water. 46 grams of sodium reacted with water. So you need to make an equation, or this you're doing Na plus H2O, right? And what you're getting is NaOH. So you should know this from the chapter of metals and hydrogen gas. And what we want is the hydrogen gas. Now, this is not balanced, is it?
Uh, it is balanced.
How is it balanced? The sodium is fine, the oxygen is fine. You've got two hydrogens here, three over here, so it's not balanced.
Mm, two hydrogens there and two is there, right? Right.
2 and 3.
We okay. Two and three. Oh, three on the product side for hydrogen.
3
Yeah.
for hydrogen?
Yeah.
Okay, so that makes it 7.
Okay, remove the three. Right.
2 on the product side for hydrogen.
2 on the product side for hydrogen. Okay, that makes it 5 on the product side. So how are you going to, make up for the two hydrogens here? They're just two hydrogens. Obviously, this is not a balancing equation question, but we're still doing that.
Like remove the 2.
Okay. What's next? 1 or 4?
One.
1's already there.
Like on the reactant side,
Huh?
2.
2 where?
Not 2, like 3
Where?
for hydrogen.
H2O on the reactant side?
Yeah.
Okay, so that gives me 6 hydrogens and 3 oxygens.
And 3 for sodium as well.
3 for sodium as well.
And 3 on the product side.
Where?
For NaOH.
So that gives me 3 oxygens, 3 sodiums, and 6 hydrogens. 3 oxygens, 3 sodiums, and 5 hydrogens. We're still not there.
Two Na
Okay.
and two H2O on the product side. Yeah, there. Okay.
Reactant
And,
side.
yeah, sorry. And two again. Here, yeah.
Yes. And this would be balanced. Now, when we are working with mass and moles, right, the equation needs to. Why did I make you balance this equation? You could have taken a look in the book. It's given as a balanced equation. But you need to balance the equation before you get into calculations, right? Because right, why do we balance it? Because it gives us the proper amounts in which different substances react, right? So you've got two atoms of hydrogen and two molecules of water, right, reacting to form two molecules of sodium hydroxide and one molecule of hydrogen. So that is, right, we look at it that way, but we can also look at it broadly, right, saying that we've got 2 moles of sodium reacting with 2 moles of water, giving us 2 moles of sodium hydroxide and 1 mole of hydrogen, right?
Yeah.
Now we have to take a look at the masses. So sodium is 23, so that's 23 into 2. Water's 18, so that's 18 into 2. Sodium hydroxide is what? 23 plus 1, 24. 24 plus 16 is 40, right? So 40 into 2, and this guy is just 2, right? And so you've got 46 and 36 and 80 and 2. Now the question is asking you what's the mass? Right, now this part, I'll put an asterisk over here. We're going to come back to this later, right? But just so that you know that in terms of moles, you can take a look at that as well. And it makes sense, right? Because why? Right? To, let's get done with this first. So we are saying they're asking about 46 grams of sodium. So the reaction, a balanced equation, does have 46 grams to start off with. And that means, according to the balanced equation, right, only 2 grams of hydrogen are produced. So that's your answer.
Yeah. Okay.
Right? Now, just to clarify what I mentioned about the, the taking a look at in terms of molecules or moles. So you've got 2Na plus 2H2O giving 2NaOH and single molecule of hydrogen. Up till now, whatever the equation we saw, we said, oh, there are 2 atoms of sodium reacting with 2 molecules of water, giving 2 molecules of sodium hydroxide and 1 molecule of. Now, whether I say atom or molecule, all of these are particles, right?
Yeah.
So they're reacting in a ratio of 2:2, giving me products in the ratio of 2:1,
Yeah.
right? I can by extension say that there are 2 moles of sodium. Why? Because 1 mole has 6.02. 1 mole has 6.02 into 10 to the power 23. So 2 moles means 12.04 into 10 to the power 23 particles. And again, 2 moles here. So again, a 12.04 into 10 to the power 23. 2 moles here. So again, right, 12.04 into 10 to the power 23. And 1 mole here, which is 6.02 into 10 to the power 23. And so again, I'm getting a ratio of 2:2, giving me 2:1. So is that any different? I mean, it's the same thing that's happening, right? It's just that what we're looking at now is, instead of looking at the simplest ratio, which is just 2 atoms reacting with 2 molecules, you have got, right, like a huge number of atoms reacting with a similarly huge number of molecules, giving you, right, all of these guys. But right, so looking at it in terms of moles and looking at it in terms like the minimum that's happening is 2 atoms and 2 molecules reacting to give 2 molecules of sodium hydroxide and 1 molecule of water. But again, right, when we are conducting experiments, we are not picking out two individual atoms. We are not picking out two individual molecules, right? We are taking larger quantities like we did over here, right? And so this is, measuring out 46 grams and 36 grams is much easier. And so when I'm taking, so with that too, right, I'm using the mole, and 1 mole is 23 grams, and so I'm taking 46 grams, right? So it's not affecting the reaction. It's just what it's giving me is I'm using those many more particles, and so the more reactants I use, the more product I'm going to get. Is this like, are you following? I'm basically trying to, you know, sort of do a recap of what we did the last time, but through this question.
Yeah.
Are you
Yeah.
following? Hopefully this is not confusing you. It's the same thing we did the last time.
Yeah.
You sure?
Yeah.
Okay. Haram?
Yes.
Okay, good. Now, similarly, right, we have a question where they're asking you, what is the mass two moles of iron and 0.25 mole of iron, right? And so we need the relative atomic mass of iron. AR of Fe is 56, I believe. Yes, 56. And so we take that in mass, and so that's like 1 mole is 56 grams. The mass of 1 mole is 56 grams. Right? And so to answer part A, 2 moles equals to 56 times 2 is 112 grams. And part B is 0.25 moles, which is 56 into 0.25, and right, that gives us 14 grams.
14. Yeah.
With that, we come to a general formula. All right, so this is formula number 1, and you should note this down separately. Are you guys making notes?
Yeah.
Right, so you need to make a formula sheet for this chapter. Right, and so this is formula number 1, and that is number of moles equals to mass of element. Let me write in brackets use. This is not given the formula, I'm just putting it there, over molar mass. Right, so just like the molar mass of calcium carbonate is 100, and for example we are using 500 grams of calcium carbonate, and so in that case, how many moles do we have? We've got, right, 500 divided by 100, which is 5 moles. Okay, so let's do a different question. So this is formula number 1 that you need to know. And so obviously you can also flip this around. Mass of the element is number of moles multiplied by molar mass, which is what we did over here, right?
Yeah.
So you can rearrange this.
Depending on what the subject is.
Exactly.
Are we gonna do another question based on this formula?
Yes.
Okay.
So they're asking you number of moles of aluminum or aluminium right? In first of all 108 grams, and secondly 13.5 grams. So applying the formula, right, you got
What's
100,
molar?
right? Aluminum is 27.
Sir, what's molar mass?
Molar mass, molar mass is the either the relative atomic mass or the relative molecular mass of the substance. So if it is an element, you'd use the relative atomic mass. If it is a compound, you would use the relative molecular or formula mass. Right, so for oxygen, it is, right, 16, and for O2 it becomes 32. Right, H2O is 18, and CO2 is 32 plus 12, which is 44. Right, so all of these masses are molar masses. All right, Haran? And these are examples of relative molecular masses. So relative atomic mass, for example, what you're doing now, if you take a look at the periodic table, the mass of aluminum is 27, right? And we take that as actual mass in grams, right? So that is the molar mass of aluminum. Just like we've done so far, that carbon is 12, right? You following, Haram?
Well, I am.
Haram, you there?
Yeah.
Okay. So aluminum is 27 grams. By the way, Sobia, Maghrib was about,
Forty.
well, no, it was about, yes, it's like a few minutes ago or so, right? So
Yeah.
not when we mentioned it.
Okay.
Okay. Uh, so digression over there. Uh, yes, so we have 108 grams, which is the mass we're using, divided by the molar mass, which is the mass of aluminum, a single atom of aluminum, which is 27. And so we get 4. So 108 grams of aluminum is 4 moles. Similarly, right, you've got 13.5, and again the molar mass doesn't change, so this is the mass you're using or you're concerned with, and this gives you 0.5 moles. Comprende?
C.
Hmm. All right, Haran, makes sense.
She said yes.
He said yes. Missed that, yes. Okay, next up is formula number 2, something that we've sort of already done, right, and which is the mass of compound equals to number of moles of compound multiplied by the molar mass of the compound. So in this case, we are talking about relative molecular mass. And if you notice, it's pretty much this. Mass of an element is number of moles multiplied by, right? So mass of a compound is number of moles of the, in this case, we're talking about not the element, but the compound. So in principle, it's the same thing. And if we move it around, we can also, so I'm putting an asterisk over here, it's given as a separate, formula. But if you just move it around, you can get number of moles of compound would be what, Sobia?
Number of what?
Number of chocolates that you're going to eat today.
One.
Just one? You're not a chocoholic?
You know what? Two. Make it two.
So you're going to have 2 moles of chocolate.
Oh yeah.
So having this formula over here at the top, how am I going to find the number of moles of a compound?
You number it. Okay. You wanna find what the number of moles of a compound, right?
Yes.
Moles. Wait. Molar mass of compound divided by mass of compound.
Mm, aren't you, confusing that? I want to make the number of moles the subject. So I'm going to
Yeah.
move the molar mass to the other side. And so it's
So
going to
mass
come,
of compound divided by or
yes,
multiply.
divided. Side
Oh, yeah.
change, sign change.
Yeah.
So it's the same thing, just written around, and so like, oh, this is new, it's not new, right? You just need to keep your wits about what they're asking you to do, right? And so the question is, right, number of moles, sorry, not number of moles, mass of 3 moles and B 0.2 moles of CO2 gas. And so obviously first what we do is MR of CO2, which gives us 12 plus 16 into 2, which gives us 44 grams, right?
Yeah.
And then you solve for part A, so that's 3 into 44. That gives me what? 120, 136? No, 32, sir. 132 grams. So that's applying number of moles times molar mass of compound. Right, so 44 times 3. And similarly, 0.2 into 44, which gives me 8.8 grams. Okay.
Yeah.
Now using the, you know, the other way the formula is written, we're going to find the number of moles. And so they're asking us to find the number of moles of magnesium oxide in 80 grams and 10 grams. So the question is number of moles of magnesium oxide in 80 grams and 10 grams. So first of all, I need the relative formula mass, to use that term, of MgO. And so that's going to give me, right, magnesium is 24 and oxygen, sorry, not multiplied, plus 16. So that's going to give me 40 grams, right? Now, one way of writing this is 40 grams. I like you guys following. I haven't lost you guys today.
Yeah.
It's 40 grams per mole. Why am I writing this? Because like, the molar, this is how you write the molar mass. Right? That the relative molecular mass is 1 mole. So every mole of magnesium oxide is 40 grams. So there's 40 grams of magnesium oxide for every mole of the substance. So if I go back, I can even write down 44 grams per mole of carbon dioxide. Right? Now I'm not writing per mole over here in these two responses, in these two answers, because 132 grams is the mass of 3 moles and 8.8 is the mass of 0.2 moles. So it is not 8.8 grams per mole. I will only use the grams per mole for the molar mass of the substance. Okay.
Yeah.
And so using that formula that we have, mass of compound divided by molar mass, and so for part A, that's 80 over 40, and so the number of moles is 2. And for part B, it's 10 over 40, and so the number of moles is 0.25. Clear?
Yeah.
Okay. Next up, since we have time, is the concept of determining the moles and volume of a gas. Moles and gases. And so why are we talking about this? We're talking about this because gases are generally not measured in mass, right? But they are measured in volume, right? Now that does not mean they don't have mass, right? So just like we talked about over here, CO2 gas, you can get this equation. I mean, you not equation, you can get this question. So, right, they can ask you, okay, what's the number of moles of this mass of gas, because they do have mass. But, right, because volume is sort of more relevant, right, as compared to solids or perhaps liquids. And so right, scientists also take into consideration, okay, so what's the volume of 1 mole of gas, right? How much three-dimensional space will 1 mole of gas occupy? And the condition is that, it should be at room temperature and pressure. So room pressure is 1 atmosphere, so that's atmospheric pressure. And room temperature is 25 degrees centigrade, right? I mean, it sort of depends, 20 to 25, but you take it as 25 degrees centigrade. So that is, I mean, according to IUPAC at least, right? So the International Union of, Chemistry stuff, that considers 25 degrees centigrade to be room temperature. So you add 1 atmospheric pressure, which is normal atmospheric pressure. So 1 atmosphere and 25 degrees centigrade, right? And under these conditions, when you have 1 mole of gas, what is the volume that you're going to find it occupying? And that is approximately what they like to call 24 dm cube. DM does not mean direct message from Instagram. Okay.
Oh, yeah.
You're not sending 3 direct messages to the gas, right? DM stands for decimeter, which translates to basically a liter, well, decimeter cube. DM cube means 1 liter, which, right, 1 DM cube, sorry, 1 DM cube. Wait, what am I doing? Yeah, sorry. So DM cube means liter, right? Which means that this is 24, it's occupying a volume of 24 liters at room temperature and pressure. So again, the carbon dioxide gas that we had, it's 44 grams per mole. And so the CO2 gas, for example, which is 44 grams per mole, is going to occupy 24 dm cube or 24 liters of volume. O2 gas, which is 32 grams per mole, sorry, not right, is also going to occupy the same volume at RTP. Right? Steam, which is 18 grams per mole, right? So the state does not affect the mass, is also going to occupy 24 dm cube at RTP. Make sense? I mean, are you following? Not so much as making
Yeah.
sense, but following?
Yes.
Okay. And so then we come to formula number 3. And that is number of moles of gas equals to the volume of gas right, which should be in decimeter cube at room temperature and pressure divided by 24 dm cube, because that is the volume of 1 mole. And again, if you want to flip it around, right, depending on what it is you're trying to find, you can do volume of gas. So what is the volume of gas a certain number of moles are occupying, right? Again, in dm cube at RTP equals to number of moles of gas multiplied by 24 dm cube. Yeah.
Yeah.
And so that brings us to a question. And that question is, find the number of moles of ammonia that's a gas which has the formula NH3 in 72 dm cube at RTP. Right, and so to find the number of moles, we do volume of gas divided by 24. And so number of moles equals to 72 divided by 24, which gives us 3 moles. Simple.
Yes.
Now,
Yeah.
I just want to sort of include over here, what's the mass? What's the mass of 3 moles of ammonia?
Mass, like
Right, and so if you go
it
back,
will be multiplied by whole mass.
exactly, and so mass of a compound is number of moles multiplied by the molar mass. So these equations are helpful. I mean, it's sort of logical as well, even if you don't sort of remember, but you understand the concept, and so you can put 2 and 2 together, right? Just like Haram did. I don't know if you recall the formula we just did, but what you can do is you can find the molar mass of NH3, and so, right, what is the mass of nitrogen? Right, it's 14, right? And so you have 14 plus 3, and that gives you 17. And so, right, you've got 17 into 3, which gives you what? 34 and 44 and 51, I believe. 51 grams. So this is grams per 17 grams per mole. And so in 3 moles, you've got 51 grams of ammonia gas. Finally, just to quickly wrap up, another question could be short, where they're asking you to calculate the volume of carbon dioxide.
So,
Yeah.
like it will be given as a word problem or just
Yes.
like normal sum.
It will give like it will be a word problem, but the numbers will be given as numbers. Right? It could be given as an individual number. It could be stepwise. So the question will have parts. The question will have parts, and they'll ask you to calculate one thing, and then the other, and the other, and they'll ask you to use each part for the next, and put those together, and then come to like a conclusion, like one final calculation. Okay. So what you need to find out the volume of carbon dioxide gas occupied, right, when they're 5 moles and 0.5 moles. So, right, what we're going to do is, for the formula, right, volume of gas is number of moles times 24. And so what you're going to do for the first one is 5 into 24, which is going to give you 120, I believe. 120 dm cube. And for part B, that's 0.5 into 24, and that's going to, oops, not multiply, that's going to give you 12 dm cube. Simple.
Yeah.
Right? And so this was also figured out by Avogadro. So not only did he give us the mole, he also gave us this law, right? And oh yeah, right? All of these are 1 mole. So all of these 40, like 32 grams of oxygen at occupying a volume. So how many particles are there in 24 liters of oxygen at RTP, which is 32 grams of oxygen, right? 6.02 into 10 to the power 23 particles. Let's not forget that. and that is called Avogadro's law, right? That equal volumes of all gases measured at the same temperature and pressure must contain the same number of molecules. Avogadro's law. Okay? Equal volumes of gas at RTP, right, have, what was it? Same number of molecules. Number of particles. Sort of squeezing that in over here. Any questions?
No.
Okay, then I'll see you guys next time, inshallah.
Okay.
All right.
Hafiz.
Allah Hafiz.
Allah.
Allah Hafiz.